Today we're going to talk about right triangle trigonometry. And so, of course, what is right triangle trigonometry? It's simply the study of right triangles. And so I'm sure you're familiar with this idea of a right triangle. You have a triangle, and it has one side or one angle is a right angle, which means it's 90 degrees. We have some properties that you should be familiar with when working with right triangles. The first one's the Pythagorean theorem, which everybody should be pretty much familiar with. The idea is if you have a side A, a side B, and a side C on a right triangle, then you have a squared plus b squared is equal to c squared. And this formula only works for right triangles. You should ask about sort of why this actually works. There's a nice little picture proof here I'm going to show you. So here I set up my this is sort of a room. So I say this is sort of like it's called a picture proof because basically watch the picture and it's going to prove the theorem for you. So I call this one a proof by moving furniture, and the idea is think about this as being sort of like a room, and you have four couches, four triangular couches. So 1, 2, 3, and 4 couches, and in the middle you have a rug or exposed carpet, let's say, and the area of the carpet obviously is c squared. Now what happens when you move these couches is that the area of the carpet should remain exactly the same because you're not changing the area at all, although the position of the couches change, or what carpet exposed is changed, the area should remain constant. So if we put this into motion, you'll watch that this couch goes over here and these couches come together, and what you notice is now this area is a squared because you have a times a, and this area here is b squared, so b times b, and you know that these areas have to be exactly the same because all you did was move furniture. Right? So this is a proof by moving furniture. So let's watch it one more time. So you move this couch over here, you move these two couches down together, and it becomes clear that here's a square that has area a squared, here's a square that has area b squared. The area should remain the same because you just move the couches, so c squared should be equal to a squared plus b squared. So that's a nice little proof by picture. Okay, so let's go back here. Also, you should know the angle sum theorem. All right, so the angle sum theorem here. What does that say? That says if you have a triangle, and you look at all three angles, so let's just name this alpha. We'll name this one beta, and then this one gamma. What does that mean? That means alpha plus beta plus gamma equals a nice number, which, if you remember, is 180 degrees. So we have these two theorems, the Pythagorean theorem, and then also this angle sum theorem here. Which tells us, again, if you add up all the angles inside any triangle, not just a right triangle, any triangle, that's gamma, inside any triangle, they always add up to 180 degrees. Since we explained this, we might as well explain this relatively quickly. You can think about this, and let's do a simplified picture. If you take this triangle here, let's just make it a right triangle. How do you know that those angles add up to 180 degrees? Well, that's because you can turn it into a rectangle by adding two sides here. And you know these are 90 degree angles, and so inside a rectangle it's 360. So it just sort of makes sense if you half it, you get 180 angles here. You can do this the same way. You could split this up into two right angles and say this is 180 and this is 180. And then if you take out these two right angles here, which is 180, you get back 180 degrees. So basically these theorems aren't too hard to prove with pictures, basically. All right, so let's do a problem using these two ideas. We're going to find the length of the side and the angle of the right triangle. So the first one length of the side. So here we want to find basically what is A equal to. It's really simple. It's just Pythagorean theorem because you have a right triangle. So let's just write down Pythagorean theorem. And let's state it again to help us remember it. So a squared plus b squared is equal to c squared. And we're just going to plug in. And so a we don't know, so we'll just keep it as a. So we have a squared. Plus b we know is 8, so we have 8 squared, is equal to c, which is 10, which is 10 squared. And so a squared plus 64 is equal to 100. And then we subtract 64 from both sides, get a squared equal to 36, and so then a is equal to plus or minus the square root of 36, but we care only about the plus part because obviously a has to be positive, and so a is equal to 6. And so this is the number 6. To figure out the angle that's missing in the right triangle, so we're missing this angle right here, let's call it theta. All right, we'll use this Greek letter theta a lot to represent an angle. And so we know from the sum angle theorem, or the angle sum theorem, what do we know? We know that all these angles need to add up to 180. So if you take 37 degrees plus theta plus, remember this is a 90-degree angle down here, so that's what this little L means. And so plus 90 degrees, this should be equal to 180 degrees. And so we know theta plus, and then 90 plus 37 is 127 degrees is equal to 180. So we'll subtract 127 from both sides, and we'll get our theta to be equal to, so I count up to 3, it gives me a 30, and so it must be 53 degrees. So that's the angle value for theta. And I guess I could have used B here instead of theta. So real quick, I did label these, I forgot. So this is actually angle A, angle B, and angle C. So if you want, we don't really need to use theta. We could actually just put a B here and use those. And remember, we know the angle sum theorem says A plus B plus angle C should be equal to 180 degrees. Right? So I didn't have to introduce that theta there if I didn't want to. But it's okay if you did. It's not a big deal. All right, so let's go back. We talked about the Pythagorean theorem. We talked about angle sum theorem. So now we want to understand these trigonometric expressions. So what do you mean trigonometric expressions? All right, so you may have heard of these before, but we have what's called the sine, the cosine, the tangent, and they have some partners over here, which we call the cosecant, and the secant, and then finally the cotangent. Now we sort of abbreviate these when we write them down in mathematics. So for sine, we write sin. When we use it for the cosine, we write cos. Of course, for the tangent, you can guess we use tan. And then the cosecant, kind of funny, we use CSC for it. And then for the secant, we use SEC. And then for the cotan, we use COT. All right, so these are what I mean by trigonometric expressions right here. And we can calculate these on our calculator. So let's take a look at the calculator. And so you'll notice on the calculator, you'll see some of these trigonometric expressions here. So here's the sine, the cosine, and the tan. Now I know you don't see the cosecant button, secant button, or cotan button, and that's because these can actually be expressed in terms of those. And we'll talk more about this later. That's when we talk about the reciprocal and quotient identity. So, but let's just do a calculator problem. So, so you can kind of see here. You can hit the sine button. It says a sine of what? You can put numbers in there. So let's put 56 in there, and hit enter, and numbers will come out. So let's do the problem on the handout here. So here's some problems, and we want to basically use our calculator to find the value of each trigonometric expression to 4 decimal places. So on here, let's hit cosine of 37. So cosine, and it's a 37 degrees. And so hit 37 in parentheses, and it spits out some number. So we'll do this to 4 decimal places. So to 4 decimal places, this is 0.7986. So this is approximately 0.7986. And that's because the 5th decimal place is a 3, so we just drop it off. Now, this is for degrees, and what you want to notice is if you hit mode, your calculator, if you didn't get that answer, you may not be in degrees, so make sure you are in degrees. But you'll notice here, tan of 3 pi over 7, now we're no longer in degrees because you see there's no little degree circle here. Now we're in radians, so we're going to switch. So I'm going to go over here and hit enter, and now I'm on radians, and I hit second mode to get out of there. And then I'll just hit tan, and I'll do 3 pi over 7. So 3, and the pi button's behind the caret button, so I'll hit second caret, which gives me pi, and then divide it by 7 in parentheses, and I get another number out. So 4.381, and to 4 decimal places, that 2 will become a 3 because that's an 8. So 4.3813. So this is approximately 4.18. What did I say here? 13. Oh, 3813. All right, so 3813. All right, so that's what that is approximately equal to that. And then we'll do one more here, the secant. Now, in order to do the secant, you'll notice that you're going to have a bit of a problem because there is no secant button on your calculator, and we'll learn what I'm about to say here. So what you'll learn is that the secant is actually 1 over cosine. So this is the same as 1 over cosine of 3 pi divided by 11. And so we can plug that into our calculator. So here's my calculator here. So I'll do 1 divided by cosine of 3, then second raised 2 to get to the pi button, divided by 11. And I'll hit enter, and so this one is approximately 1.527. So here's approximately 1.527. I guess we'll put a 0 here since it did say to 4 decimal places. Right, and I'll explain why that is in a little bit. But that's how we do evaluate these trigonometric expressions with our calculator. Now, of course, we want to understand what do these numbers actually mean. Right, so just like we did with the log, like when I said something like, hey, ln of 5, I can find that on my calculator. I just do ln of 5, and I hit enter, and that spits out this number 1.609, so approximately 1.609. But what does that number mean? Right, so what does this number mean? Right, this is the number you raise e to get back 5. So you'll notice if you take second ln and second answer, you do get back the number 5. So we want to do something similar over here to try to understand what these numbers are. And to do that, we need to talk about the definition of these trigonometric expressions. So how are they actually defined? For the logarithm, remember, for a logarithm, it was defined like this. If you had log base b of x equal to y, it was defined, this says b to the y is equal to x. Right, but how do we define the sine, the cosine, the tan, the cosecant, the secant, and the cotan? It's actually not very hard. Of course, we're going to use triangles, and specifically a right triangle. And you can do this by memorizing a real simple saying. So ka toa. And there are all kinds of ways to memorize this. I think my high school teacher one time said some old hippie caught another hippie tripping on acid. That was one way to memorize it. Another teacher taught it to me, saying you're walking down the street and you stub your toes, so you need to go soka toa. It's all kinds of silly ways to remember it. But the idea of the so is that the sine of an angle, so this is any angle theta, what the sine of an angle actually is, it's the opposite side over the hypotenuse. It's the SO part. So the opposite side, which is the length of the opposite side, so you can measure this length and get a number out, divided by this length, and you get a number out. So divided by the hypotenuse, the length of the hypotenuse. Whereas the cosine is the ca part, and the A stands for the adjacent side to the angle. So if you have theta, right, you have the opposite side to theta, and you have the adjacent side. So opposite, of course, is on the other side of theta, and then the adjacent is the side next to theta, and of course the hypotenuse is the longest side of a triangle. And so here you take the length of the adjacent side, I'm just going to abbreviate it like this, and divide it by the length of the hypotenuse, so whatever that is. And then a tan of theta is the TOA, which is the opposite side over the adjacent. So the length of the opposite side divided by the length of the adjacent side. And then the cosecant, secant, and cotan of theta, these are just the flips of the ones next to them. So the cosecant of theta is the flip of this. So it's defined to be the length of the hypotenuse over the opposite side. And the flip of this, right, the reciprocal of this is the secant of theta is the hypotenuse over the adjacent. And then finally the cotan of theta is reciprocal of the tan of theta, so it's the adjacent over the opposite. So once I know these, I get these for free. Now I do have to remember that, sine of theta and cosecant theta kind of go together, and the way I remember that is that you have a C here and an S there, so it's opposite the letters go together. So cosine of theta and secant theta go together. And of course you really don't have to memorize how tan and cotan relate, because the names themselves sort of pair them up. So real quick, in the problem we did before, we got the cosine of theta, or of not theta, but of 37 degrees. Of 37 degrees to be approximately 0.798. I think it was 6. Right, so 986, yeah. So 986. So what does this number mean? Right, so how do you explain it to somebody? And it's not hard to do. So the idea is if you had a right triangle, so if you construct a right triangle, so this has to be 90 degrees, and this angle here happens to be 37 degrees, if you took a ruler and you measured the adjacent side, so whatever that length was, right, so some number, and then you divided it by the length of the hypotenuse. So you took a ruler out again and you measured this side, you get out another length, and the ratio of this red number to this green number would be about 0.798. So approximately 0.796 if you measured it really closely. So this is just the cosine of that angle, 37 degrees. Is equal to the length of the adjacent side to the angle divided by the hypotenuse of the triangle. And so you can explain all these different things, like if you took the tan of 37 degrees, right, your calculator would spit out a number, right? So the tan of 37 degrees, so tan 37, it spits out a number, right? And it spits out actually a negative number. Right? So here you have to be careful, right? Because when I plugged in 37, I'm like, well, it shouldn't be negative. I mean, it should be positive, shouldn't it? I mean, it's like the opposite side over the adjacent side. But what happened here is that, if you remember, my calculator is no longer in degrees. It's actually in radians. So we want to fix that. We'll talk about what happens when the tan becomes... What happens when you take the tan of an angle and you get a negative number. But I don't want to talk about that right now. So I need to change this back to degrees. So hit Enter, and then second quit. Oops. I think I crashed this program. Hold on. So let me open it up again. All right, let's try this again. So Enter, right, second quit. Take the tan of 37 now. You'll see you'll get a different answer because now we're not in radians. We're actually in degrees. And I get out this answer of 0.7536, right? So this is 0.7536. So again, what does that number mean? It's not hard, right? If you just think about it, so what does it mean? It means if you took the opposite side here and took a ruler and you measured it, you would get out a yellow number. And then if you divided that number by the adjacent side, so that red thing, right, so whatever that red number was, and you took that ratio there, the yellow number divided by the red number, then it would be approximately 0.7536. And so that's the idea. Another thing students often will ask is, why are there just 6 trigonometric expressions? So why 6? And if you think about it, you have 1, 2, 3 things. You have an adjacent side, opposite side, and hypotenuse side. How many different ways can you divide those 3 things? And if you write them all down, you'll see that there are just 6 ways to divide those 3 different things. That's why there are only 6 trigonometric expressions. All right, let's move on. Let's use this, what we just did, to do something. Okay, so example 4 says, use the Pythagorean theorem to find the length of the missing side of the right triangle. So you see you have 10 and 6, and so you have a missing side here. We call it, if you want, B. So we want to find what B is equal to. And then what else? Then find the values of each of the 6 trigonometric expressions. So we want to find then sine of theta, cosine of theta, and tan of theta. And notice how I write these up. I write them up the same way each time. So I want to find out what those are. And then I can find their flips by simply flipping them. So this would be the cosecant of theta, and then the secant of theta, and then finally the cotan of theta. So those will be easy to find because they'll just be the flips of these. All right, so let's find B first, and then we can kind of go through and talk about how do you find those. So how do we find B? We're going to use a Pythagorean theorem like it says. And so I know the Pythagorean theorem says a squared plus b squared is equal to c squared. Now I know a is 6, so this will be 6 squared. I don't know what b squared is, so I'll just leave it alone. So plus b squared is equal to, and then here's 10. So 10 squared. And so I get 36 plus b squared is equal to 100. I subtract 36 from both sides, and I get my answer of b squared equal to what? So 64. Yeah, 64 sounds good. And then you take the square root, and so b is equal to plus or minus 8, but of course b is positive because it's the side of a right triangle, so b has to be equal to 8. So b is equal to 8. So this question mark is actually in 8. Once I know that, I can SOHCAHTOA this. Okay, so remember that saying, SOHCAHTOA. I don't want to memorize too much. I just want to memorize the minimal amount and then try to think about how you use that to solve these types of problems. So the sine, remember, that's the SO. It's the opposite over the hypotenuse. So here's my angle theta. And let's clean this up just a little bit. So let me erase this and let me erase this. And so remember what the opposite side is. So this is the opposite side of theta. This is the adjacent side of theta. It's the side next to theta. And then, of course, this is the long side, so it's the hypotenuse. And the sine of theta is the so it's the opposite over the hypotenuse, so it should be 6. That's the opposite side. And then the length of the hypotenuse is 10, which reduces to, they're both divisible by 2, so 3 over 5. And the cosine, that's the part, so the adjacent over the hypotenuse. And now the adjacent side we just found was 8. And the hypotenuse is 10. And so that reduces to 4/5. And of course, tan of theta is the TOA part. And TOA means opposite over adjacent. And so it's 6 over 8, which is equal to 3 over 4. And then finally, these over here are real simple to find. Cosecant of theta is the flip of sine of theta, so it's 5 over 3. And secant theta is the flip of cosine of theta, so it's 5 over 4. And cotan of theta is the flip, or if we want to be fancy, the reciprocal of tan of theta, and so it's 4 over 3. And so that's how you figure out the value of these 6 trigonometric expressions. All right, so moving on, what do we have left here? So we talked about the definition. How do we define the sine, cosine, and tan, and so on. And then now we want to talk about a couple identities we're going to use throughout the rest of this course called the reciprocal and quotient identities. They're really pretty simple to remember once you get the hang of it. And so here we have what are called the reciprocal identities, which you could also just call, if you want, the flip identities. It just tells us how to express cosecant of theta, secant theta, and cotan theta in terms of sine of theta, cosine of theta, and cotan of theta. Namely, cosecant of theta is the flip of sine of theta, so it's 1 over sine of theta. And secant theta is the flip of cosine of theta, so it's 1 over cosine of theta. And cotan of theta is the flip, or if we want to be fancy, the reciprocal of tan of theta, so it's 1 over tan of theta. And so that's the idea behind that. And the quotient identities, right, they're called quotient because you are going to divide 2 trigonometric expressions. Namely, it allows us to express tans and cotans in terms of sines and cosines. So the tan of theta actually turns out to be the sine of theta over the cosine of theta. And to see that's not hard, so remember how we define sine of theta. It's equal to the opposite side, the length of the opposite side divided by the length of the hypotenuse. And the cosine of theta, basically the same thing, except the opposite side, you take the adjacent side divided by the hypotenuse. And then the tan of theta was equal to the opposite over the adjacent. And so what you want to notice here is that we can use these 2 expressions to create this expression. And it's really easy. You just take this and divide by that. So if you took the opposite over the hypotenuse and you divide it by the adjacent over the hypotenuse, what happens is, remember, when you divide by a fraction, you multiply by the reciprocal, so the hypotenuse will cancel. So the reciprocal of the adjacent of hypotenuse is hypotenuse over adjacent. And of course, these cancel, and you're left with the opposite over the adjacent. So you can use the sine of theta and the cosine of theta. If you divide them, you get back the tan of theta. And of course, then the cotan of theta is just the flip of that, just the reciprocal of it. So you get the cosine of theta divided by the sine of theta. And so we call these the quotient identities because you're using the sine and cosine by dividing, by taking their quotient. And we're getting back tan of theta and cotan of theta. And so the whole point of these are basically to understand that all the secant, the cosecant, and the cotan can be expressed in terms of sines, cosines, and tans. But the tan and the cotan can also be expressed in terms of sines and cosines. So in essence, all we really care about are sines and cosines of angles. And if we understand those completely, then we can understand all the other trigonometric expressions that we have. All right, so we want to finish this lecture with an application. And so let's take a look at the problem we're going to do. And so what we have here is sighting the top of a building. The surveyor measured the angle of elevation to be 22 degrees. And notice they give us the picture. So here's that 22 degrees right here. And here's that person right over here. The transit is 5 feet off the ground. So the transit is this device that the surveyor is using to figure out the height of this building. So they label it here. So this 5 feet right there above the ground. And 300 feet from the building. So 300 feet from the building. So from here to here, it's 300 feet. And we want to find the building's height. So the picture is basically given to us. We want to find the height of the building, which is actually, they give us h. So find h. So this is what we're actually looking for. And so in order to find h, what we first need to do is just find a right triangle and see if we can't use that to do something. So here's the right triangle. They actually draw it for us with this dotted line. And you have to be careful because the right triangle actually doesn't involve h. But h is related to the height of the right triangle. Let's pretend that's a straight line. Because they label the height of the right triangle here a. And we know, so for our equation, we know that h is equal to a, but you have to add on this extra 5 feet. Right, so there's a little bit of extra footage here. So right here, you have to add on the extra 5 feet. So it's enough to go and find a, and if we can find a, we can find h. So let's do that. We know how to find a. How do you find a? Well, it's a right triangle. We're looking for this side. We know this side is 300, and we know the angle is 22. So 22, opposite side, adjacent side. Is there any trigonometric expression we can use, this is the question you want to ask yourself, that would involve the opposite, adjacent, and the angle? And so if you get stuck, just write down SOHCAHTOA, the definition of these trigonometric expressions. And you're like, oh, the TOA involves the opposite and the adjacent. So we know that the tan of the angle, right, so tan of 22 degrees, is actually equal to the opposite side over the adjacent side, so a over 300. And we can solve this equation by getting rid of the divided by 300. So we multiply both sides by 300, and so we get 300 tan of 22 degrees is equal to a. And so over here, now I know that h is equal to 300 tan of 22 degrees plus 5, and this should be in feet, which is approximately, so let's go to my calculator to check it out. So approximately on my calculator, now make sure you're in degrees, so when you turn it on, hit mode, and make sure you're actually in degrees. So I'm in degrees, so I should be good to go. And so I get 300 tan of 22 in parentheses, and then I'm going to add 5, and I get my answer of about 126 feet. So this is about approximately 126 feet. So that's the height of the building. So quickly here, let's just sort of recap what we've just done in this video. So we talked about, what is right triangle trigonometry. It's really just a study of right triangles. It turns out basically, if we understand right triangles, we understand all triangles in general and their properties. Because if you draw any sort of triangle, it doesn't have to be right. And so here's a strange looking triangle right here. But what we can do is we can simply create two different right triangles out of that one triangle. So in essence, every triangle can be reduced down into terms of right triangles, and we can use the properties of right triangles to understand properties of triangles in general. So that's sort of the idea. When working with right triangles and triangles in general, remember the Pythagorean theorem for right triangles and the sum angle theorem, or the angle sum theorem for triangles in general, which means all the angles add up to 180 degrees. We talked about evaluating trigonometric expressions. So it's really important that if you take the sine of an angle like 37 degrees and you get back a number, then you understand what does that represent. You can actually give sort of a physical interpretation of that number from, constructing a right triangle with an angle here of 37 degrees and saying, hey, this number, sine of 37 degrees, whatever number you get out on your calculator, it's really the length of that opposite side divided by the length of the hypotenuse, because we have this sort of SOHCAHTOA, right, which is how we define, those 6 trigonometric expressions: the sine, the cosine, the tan, the cosecant, the secant, and the cotan. We talked about these reciprocal and quotient identities. So we're going to use a lot of those later. It's easy to remember them if you think about it. So how do you know what the cosecant theta is? Well, this is a c, so it's opposite the letter, so that's 1 over sine of theta. And of course, if you know this one, you get the secant of theta for free. And it's equal to 1 over cosine of theta. Again, it's opposite the letter in S, and so C. And then finally, the tan of theta, or you can write that as, or the cotan of theta you can write as 1 over tan theta, but the tan of theta is actually sine of theta over cosine of theta. I don't have a neat little way to memorize this. I just always know it's the sine of theta over the cosine of theta. That's how I remember it. Other than that, we did some applications, which we just did that example, so it should be you should be good to go.